Hello everyone, Mr. Fawcett here, and we are back with another AP Calculus lesson. Today we're going to finish up our discussion of differential equations and talk specifically about how to model real-world scenarios with differential equations. Before we get into those specific types of problems though, let's review what directly proportional and inversely proportional mean, because these words are going to pop up later on in our lesson today. So if I want to say that y is directly proportional to x, then algebraically, I would say y is equal to some constant times x. So k is generally what we use when we're talking about the constant of proportionality. All that means for every x and y value that we're going to use here, right, if I divide y by x, that's always going to come out to be k. So the ratio of all the y and the x values that work here, they're going to be the same. They're going to have the same ratio. Inversely proportional means that y is equal to 1 over x times k. Or we could say k over x. So what this means is that if you multiply x and y together, so if you did y times x, that would always give you the same number for every x and y value that work in that equation, obviously. Okay, so let's use these relationships, just write some simple equations. Pause the video, see if you can write equations based on what 1 through, let's actually do 1 through 6, so 2 on the next page as well. Well, y is directly proportional to x, or sorry, w is directly proportional to x. That means w is equal to k times x. H is inversely proportional to y, so we have h is equal to k over y. You could also do k times 1 over y times k, etc. Number 3, x is directly proportional to the square of y. So I have x is equal to k, and then instead of y, I just have y squared, directly proportional to the square of y. For number 4, it says c is inversely proportional to the square root of y. So c, inversely proportional, so k over, but instead of k over y, I have k over the square root of y. Let me scroll down here actually, because I need a bit more room here. 5 and 6 are slightly different from 1 to 4, whereas you're actually going to have to figure out what the constant of proportionality is here. Whereas in 1 through 4, we just let it be represented by k. In 5 and 6, we actually need to figure out what that is. It's kind of like being given an initial condition with the differential equation and figuring out what that c value is. So it says x is directly proportional to y. So I have x is equal to k times y. Now it says when x is equal to 9, y is equal to 15. So when x is equal to 9, y is equal to 15. And if I want to solve for this k value, I'm going to get 9/15 is equal to k. Might as well simplify. So I'll get 3 over 5 is equal to k. So our new equation becomes x is equal to 3/5 times y. So we know that our constant of proportionality is 3/5. For number 6, it says y is inversely proportional to the square of x. So we have y inversely proportional, so k over the square of x, so x squared, not the square root of x. And when x is equal to -8, y is equal to +12. So I get 12 is equal to k over -8 squared. That gives me 12 is equal to k over 64. You may have to break out your calculators here. 64 times 12, let's actually see, that should be 640, 768 is equal to k. So my final equation becomes y is equal to 768 divided by the square of x, or x squared. Okay, so even though those were some word problems, not really real-world scenarios, they were just working with variables, let's move on to some real-world scenarios and also some differential equations. All right, so it says a rumor spreads among a population of n people at a rate proportional to the product of the number of people who have heard the rumor and the number of people who have not heard the rumor. If P denotes the number of people who have heard the rumor, which of the following differential equations could be used to model this situation with respect to time t, where k is a positive constant? If it doesn't say inversely proportional, you can assume that it means directly proportional. Okay, so I know it just says proportional, so you can assume directly. Okay, let's try to break this down. So we are looking for, it says a rumor spreads among a population of n people. So we're looking for the rate at which the rumor spreads. That's going to be represented by dp dt, because p represents the number of people who have heard the rumor. So the change in p over the change in time. dp dt, that represents the rate of the number of people that have heard the rumor. So dp dt, it says that is proportional to the product of the number of people who have heard the rumor. And first of all, I can put my k here because I know that's the constant proportionality. So the product of the number of people who have heard the rumor, well, the number of people that have heard the rumor, that's p, right? So k times p times, because it's a product, the number of people who have not heard the rumor. Well, if p is the number of people that have heard the rumor, and n is the total population, what's an expression for the number of people who have not heard the rumor? Well, that would be n minus p. So let's label what the different parts of this equation represent. We have the blue, rate at which the rumor spreads. We have k, constant of proportionality. I don't think I need to label that. P, number of people who have heard the rumor, and n minus p, number of people who have not heard the rumor. My goodness. Okay. So again, if you're not sure where those pieces came from or why we wrote those down, go back and look at what the problem is telling us. I know there's a lot there, but try to break it down and see how we come up with our equation. Well, now hopefully we have an equation that matches that, right? Excuse me. And that equation ends up being C. That is the one that matches the one we came up with. All right, let's look at another one. So it says the rate of change of the volume of a water in a tank with respect to time t is directly proportional to the square root of the volume. Which of the following is a differential equation that describes this relationship? Well, the rate of change of the volume, and maybe this brings us back to related rates. Rate of change of the volume wouldn't be v, it would be dv dt. So we'd start with that, dv dt. It said is directly proportional, so k times the square root of the volume. Well, the volume's v, so the square root of v. And that's all. That's it. A little bit less complicated than the one we did before. So we have square root of volume we have our constant of proportionality, and we have the rate of change of volume. So this one should be E. dv dt is equal to k times the square root of v. All right, let's go ahead and do, I think, 3 more. We're going to do 6, 7, and then the very last one. Pause the video. See if you can figure out 6 and 7 on your own. I think 7's a little, I don't know actually which is going to be tougher for you. But again, see if you can write these on your own and then come back and see where you may have gone wrong, if at all. Okay, so it says a habitat of prairie dogs can support M dogs at most. The habitat's population P grows proportionally to the product of the current population and the difference between M and P. So when it says the habitat's population P grows proportionally, we're looking at the rate of change of P. So in this case, dp dt. If it just said the habitat's population P is proportional, then you would just have P is equal to something. But it says it's growing proportionally, so we're looking at the rate of change. Proportional, so we have our constant of proportionality K, to the product of the current population. Well, the current population is P, so K times P, times the difference between M and P. Difference implying subtraction, so M minus P. And there we go. Number 7 says a radioactive material decays at a rate of change proportional to the current amount, Q, of the radioactive material. So the radioactive material decays at a rate of change. So the radioactive material Q, we're looking at the rate of change of that, so dq dt. And it says it's decaying. So that means that it is decreasing that amount, which means this rate is going to be negative, right? Because the amount of Q, the amount of radioactive material, is getting smaller. So the rate at which it's changing should be negative. This is decaying at a rate proportional, so K, proportional to the current amount, Q. So just K times Q. Again, I think the key here was to understand that it's got to be negative K times Q because the amount of material is decaying, so the rate of change is going to be negative. Let's finish off with one where we actually have to go ahead and solve as well as setting it up. During a certain epidemic, and this would be a calculator. I'll actually figure this out once I read it. I think it is going to be a calculator problem, though. During a certain epidemic, the number of people that are infected at any time increases at a rate proportional to the number of people that are infected at that time. If 1,000 people are infected when the epidemic is first discovered, and 12,000 are infected 7 days later, how many people are infected 12 days after the epidemic is first discovered? All right, a lot of information here. Okay, I'm going to give you a hint in the form of what variables to use. Then I'm going to let you guys try to work this out on your own. So first thing that I want you to think about is we need a variable for the number of people that are infected at any time. So let P represent number of infected people. And let T represent time since epidemic was discovered. So those are the two variables you're going to use. First things first, see if you can set up a differential equation to represent this scenario. Then you're going to have to solve the differential equation, come up with a general solution. Once you come up with a general solution, you will have actually two variables. You'll have the constant of proportionality you'll need to solve for, and you'll have your C value, the constant of integration. You are given essentially two things that you can use to help you figure out those two unknowns. You know, the 1,000 people are infected initially, and then 1,200 people are infected 7 days later. So again, play around with it, pause the video, see what you can get, and eventually, once you have your particular solution, you'll then use that to figure out how many people were infected 12 days after the epidemic is first discovered. Okay, so if I know that P represents the number of people infected at a certain time, and T represents time, in this case days, well, we're looking for the rate of increase of the people that are infected. So it's going to be dt. That rate is equal to, or it's proportional to, the number of people that are infected at that time. So K times P. Now, we need to try to go ahead and find a general solution to this differential equation. So you have two variables that you'll be integrating with respect to. One is T, one is P. So let's get the P's on the same side as the dP, and I'm actually just going to leave the K on the other side. So I'm going to get 1 over P dP is equal to K times dt. Now, K is not a variable you are integrating with respect to. You are still integrating the right side with respect to T. So K is going to act as a constant, which means on the left-hand side, we're going to get the natural log of the absolute value of P is equal to K times T plus C. Again, you could just think of this K as being like 5. If you integrate 5 with respect to T, you just get 5T. Now, again, here we have two variables, right? We have a C and a K, or two unknowns, I should say. A C and a K to solve for. Well, if I was just given one initial condition, that wouldn't be enough. So I'm given two because I have two unknowns. So I'm going to use the first one. It says 1,000 people are infected when the epidemic is first discovered. Well, when it's first discovered, T is equal to 0. So T is equal to 0 here. So come up here. I have P is equal to 1,000. T is equal to 0. So I get the natural log of 1,000. I don't need the absolute value signs anymore because 1,000 is already positive. That is equal to K times 0 plus C. So my C value is actually the natural log of 1,000. So let's go ahead and substitute that into our equation. Natural log of the absolute value of P. And to be fair, in this case, the number of people that are infected are always going to be positive. So you don't need the absolute value signs here. You can get rid of those. It's not going to hurt if you have them. I'm just explaining why I'm not going to use them anymore. So the natural log of P is equal to K times T plus the natural log of 1,000. Now my other condition is that 1,200 are infected 7 days later. So I get the natural log of 1,200 is equal to 7 times K plus the natural log of 1,000. Well, now I just have to simplify. If I subtract the natural log of 1,000 from both sides, I can think about logarithmic rules. If I subtract two natural logs together, I can just divide the input to both of those. You know what? I'm going to come over here now, up here. So this is going to give me the natural log of 1200 divided by 1000 is equal to 7 times k. We'll just do some simplifying here. So I'm going to get the natural log of 1.2 divided by 7 is equal to k. Now, this would be a calculator problem. So you can either leave that exactly for k as an exact answer, or you could round that to we say 4 decimal places, because at the end we'll want to round to the nearest whole number. It's not going to matter too much. And you know what? We will do that just to make it a little easier on us. So natural log of 1.2 divided by 7, that gives us approximately 0.0260. So that's our approximate k value. So our particular solution here is the natural log of p is equal to 0.026 t plus the natural log of 1000. And then if we wanted to get p by itself, we would just e both sides, and that would leave us with p is equal, and approximately equal to, because we rounded our k value, but for all intensive purposes, p is equal to e to the power of 0.026 t plus natural log of 1000. Yes, you could simplify this even further and get 1000 times e to the power of 0.026 times t. Again, you're going to have to use this equation, so it doesn't really matter how much you want to simplify it, because you're going to have to use it to find another p-value anyway. Final step. We're trying to figure out how many people are infected 12 days after the epidemic is discovered. Let's substitute in 12 for t. So at t equals 12, p is approximately equal to, and we are rounding to the nearest person, and that gives us approximately 1,366, which is choice, or depending on how you rounded that k value, you're going to be somewhere near 1,367. They're not going to give you two values, 1,366 or 1,367. They're going to be far enough away to where, if you rounded to 3 decimal places versus 4 versus kept it exact, you're going to still get the correct answer. So you can see quite a bit of work. Looks even more all over the place because I had to erase and move stuff around. But this would be a reasonable question to be asked on the AP exam. To be asked to set up the differential equation, be asked to find a particular solution to the differential equation, and then being asked to use that solution, to find a certain value. So we're kind of putting everything together that we've done, except for slope fields, in our differential equations lessons to be able to answer this word problem. Okay, we are going to end the video there. We'll get some more practice both setting up differential equations to model scenarios, as well as doing other problems like this where we have to go ahead and solve them, find particular solutions, etc. But for now, enjoy the rest of your day, and we will look forward to seeing you next time.